Hello, dear students. Today we'll see the behavior of the conductors in the electrostatic fields. In electrostatic field we place some conductor, what would happen to the free electrons of the conductor and how the different properties would be associated with the conductor when it is placed in the electrostatic field. So let us see. First is the net electric field intensity in the interior of the conductor is 0. Means when the conductor is placed in the electrostatic field, then field intensity in the conductor will be 0. Means there won't be any field existing inside the conductor. So net electric field would be 0 inside the conductor when it is placed in the electric field. Why is it so? So let us consider this conductor is there, and let us consider the conductor is placed in the uniform electric field, and you see, because this is a uniform electric field and conductor is having the free electrons. So free electrons of the conductor, they will be attracted towards the positive of the field. So all these free electrons they will be accumulated here on this face, which is nearer to the positive side, and positive charges they will get accumulated here, or in other words we can say all the electrons of this conductor, they are coming to this side, leaving behind the positive charges. So another electric field is going to develop inside the conductor. You can see here outer electric field is in this direction from left to right, but because of the movement of the free electrons of the conductor, charges appear on two sides of the conductor, and electric field inside the conductor is opposite to the field which is outside. Now you see, we know that in case of conductors there are large number of free electrons. So free electrons will keep moving opposite to the field till the field inside the conductor becomes equal to the field outside. And you see, when both of the fields they will become equal, then net field inside the conductor will become 0. So that is why field inside the conductor would become 0. And you see, the motion of the electrons will be continued till there is difference in the two fields, because if field difference is there, net force would be there on the electron, and electrons will keep moving. So when the both fields are becoming equal, net force on the electron will become 0, and then electron will not be moving from one side to the other side. Then in that case the motion of the electrons will be stopped and net field inside the conductor would become 0. So in equilibrium conditions we can say both of the fields inside and outside will become 0, or net field inside the conductor will become 0. Second property is electric field just outside the charged conductor is perpendicular to the surface of the conductor. So in the first property, in first case we have seen inside the conductor electric field is 0, but outside the conductor field is not 0. Field would be there because of the charges are there on the conductor. So what is the direction of the electric field just outside the conductor? So that would be direction of the electric field would be perpendicular to the surface of the conductor. Now let us consider, so contradiction, with contradiction we are going to prove this. Let us consider we are having this conductor and it is having this small positive charge, and let us consider this is the direction of the electric field due to this charge. Now this is one normal direction. Now you see, this n cap is what? This is the direction which is normal to the surface of the conductor at this particular point, and another white vector here is showing the direction which is tangential to the conductor. So means what we have considered here, the field is not perpendicular. So on contrary basis we are going to consider that field is not perpendicular. So if it is not perpendicular, it would have two components of the electric field. One is perpendicular to the surface, other is parallel to the surface or tangential to the surface. So in that case, you see one component which we are getting along the tangent of this surface. So means the electron or the charges which are present here, they are experiencing the force due to E cos theta component. So these charges, they should start moving on the surface because of the forces being applied on them. But in actual practice, there is no surface current in electrostatics. So we can say that as the charges are not moving, so there is no force acting along the tangential direction, or in other words, we can say electric field along tangential direction is zero. So whole of the field is perpendicular to the surface of the conductor. Third point, net charge in the interior of a conductor is zero. So you can see here when the charges are given, charges are temporarily separated, the total charge of the system is zero. So you see this is the condition of the conductor when it is placed in the electric field, and because of the movement of the electrons, they would move towards the positive of the electric field, leaving behind the positive charges. So these charges, they will get separated when the conductor is placed in the electric field, and you see net charge on the conductor would be zero. Now you see, using Gauss's theorem, we have to prove that inside the conductor there is no charge existing. Now using this Gauss's theorem, we know that the flux or surface integral of electric field is q net over epsilon naught. Now in the last case we have proved, in the first case we have proved that electric field inside the conductor is zero. If electric field inside the conductor is zero, then charge inside the conductor would also be zero. So fourth point is, charge always resides on the surface of the conductor. Means whenever any conductor is given to some charge, it will always reside on the surface of the conductor. For example, this is the charge Q, this is the conductor which is attached here with this hinge and some insulated thread, and some charge we are going to give to this conductor. Now you see, when the charge is given to the conductor, it will reside only on the outer surface of the conductor. As you see, net charge inside the conductor would be zero. So charge is going to reside only on the outer surface of the conductor. Now you can see here, if we have given charge Q inside the conductor is zero, we can draw a Gaussian surface just inside the conductor. Since E is equal to 0 in the interior of the conductor, so charge inside the conductor is also 0. So means charge will remain only on the surface of the conductor. Fifth point is, electric potential is constant for the entire conductor. Electric potential is constant, as we know that electric field is the potential gradient, or we can say that dV is equal to minus ETR. Now E is what? E is 0 inside the conductor, in the interior of the conductor. So if E is 0, or we can say dV is 0, differentiation of any constant quantity can be 0. So V here would be constant. So it means the electrostatic potential inside the conductor would always be constant. So next point is, surface charge distribution may be different at different points. Now surface charge distribution, we know that when the charge is distributed on the surface, it would have the surface charge density. Now depending upon the shape of the conductor, the surface charge distribution may be different at different points. So you can see here, charge is uniformly distributed And surface charge distribution, here sigma is maximum, it is at the pointed tip, and here tip is not pointed, it is having more area. Here sigma is minimum. As we know that sigma is what? Sigma is surface per unit, charge per unit surface area. So where the surface area is less, sigma would become more, and where the surface area is more, then sigma would become less. So every conductor is an equipotential volume 3-dimensional rather than just an equipotential surface or 2-dimensional. So whatever the conductor we can consider, that would be equipotential volume, not equipotential surface. So because it can occupy some space, it is having some volume. So that's all about this properties of the conductors when they are placed in the electrostatic fields. Thank you.